Let's just suppose that we have a cube and that all edges of this cube are expanding at a rate of 3 centimeters a second. How fast is the volume changing when the length of each side is, I want to look at this at 2 centimeters and 7 centimeters. So first of all, let's draw a picture. Whenever I'm working on these types of problems, if at all possible, I'll draw a picture to help me visualize what it is that I'm actually trying to do. So I have this cube, and I know that the length of each of these is S. The length of the side, that's why I picked S. You could have picked X, doesn't really matter. The volume is then going to be S cubed. That's how you find the volume of a cube. So the edges of the cube are expanding at a rate of 3 centimeters per second. So this is telling me that ds dt, which is the rate of change in the length of the side, which is the edges, with respect to time, equals 3 centimeters per second. It gave me the rate of change of the edges of S. So what I want is, I want the rate of change of volume with respect to time. Now, S is actually a function of t. So this will be implicit differentiation, 3s squared ds dt, because S is a function of t. It's some type of implicit function of t. Now we know ds dt equals 3 centimeters a second, so I can substitute that in, and that will give me 9s squared centimeters per second. I'm going to keep my units with me here for a few steps, actually probably all the way through. Now what's being asked is, what's the rate of change of volume? Because remember, this is dv dt. What's the rate of change in volume with respect to time when, and I was given these two different lengths. Well, if I substitute in 2 centimeters for S, I will get 9 times 2 centimeters squared times centimeters per second. This is 9 times 4 centimeters squared times centimeters per second. So this is 36 centimeters cubed per second. So this thing is changing, the volume is changing at a rate of 36 cubic centimeters every second at this moment. That's the instantaneous rate of change. When I'm at 7 centimeters, this is going to be 9, I'm going to use this one again right here, 9 times, and now I have 7 centimeters squared times centimeters per second. So this equals 9 times 49 centimeters squared centimeters per second. So this is going to equal, let's see, 441 cubic centimeters per second. So the rate of change in volume when the length is 2 centimeters is 36 cubic centimeters, and when the length is 7 centimeters, it's way up here at 441, which makes sense because the area or the volume is much more bigger to begin with. So the rates of change are different at different times. Because if we could go back easily, it's not a hard calculation. If we know that we're changing at 3 centimeters per second, we can actually come up with the time that we're at 2 centimeters, 7 centimeters, assuming we start at 0 centimeters, just a dot when time is 0. And then as time expands, we get this teeny little cube that's growing, and it's getting bigger. I'm kind of messing up my picture here a little bit. Something like that. Well, you get the idea. It's getting bigger and bigger and bigger as time moves on. And as it's getting bigger, every second I'm increasing more and more volume. So this type of answer for instantaneous rates of change actually makes a lot of sense. I would expect it to have been much bigger at 7 centimeters than I would have at 2 centimeters.